Good evening, everyone. Welcome to NPTL tutorial session for the course Classics in Total Synthesis. Myself, Sreelekshmi S. I am a PhD research scholar in Indian Institute of Technology, Bombay, under the guidance of Professor Krishna P. Kaliappan. So, this is our 10th, not 10th, 11th tutorial session. So, it means it is our second last tutorial session for this course, Classics in Total Synthesis, which is taken by Professor Krishna P. Kaliappan, Department of Chemistry, IIT Bombay. Okay, so if you have gone through the last tutorial session video, which is already available in YouTube, we have completed the discussion up to week 8 assignments along with the summary lectures up to week 9 lectures. So today, week 9 and week 10 lectures was the last week's content. Yes, lecture 46, 47, 48, 49. So that was our last discussion, that is up to Taxol, and then we discussed some questions from week 9 assignment as well. But due to the lack of time, we couldn't complete the discussion on week 9 assignment. I think we have explained till fourth or fifth question, if I am correct. So today we will be continuing first the discussion of week 9 assignment. Once we will finish the week 9 assignment, then we will move to week 10 assignment as well as the content of week 11 lectures. That is lectures 50, 51, 52, 53 and 54. So that is how today's session is planned. So we will wait for a couple of minutes to see whether someone is joining or not, and then we will start our session. So I think our last discussion was for the fifth question or sixth question, and we will start right from the sixth question. So the question was identify the major product in the following sequence of reaction. So this particular diazo compound upon treatment with this hydroxyalkene and dirodium tetraacetate and toluene reflux condition in the first step, and then it is treated with BF3 etherate in benzene condition. So, what will be the major product for this reaction out of the four options given here? So, what will be happening in the first step and second step, and which will be the major product in this reaction? So here the correct answer is option D. So the correct answer for this question is option D. As we can see, first what is happening is this will form a carbenoid type of intermediate with this dirodium tetraacetate, to which this alkene get inserted through this alcohol, and we will get this particular intermediate. So let me explain that once. Okay, so this alcohol or lone pair of this oxygen will go and attack this carbon center, and this nitrogen, being a stable molecule, will get eliminated, and we will get this particular intermediate in the first step. And in the next step, what is happening is it get rearranged. That is, here as a result of this oxygen lone pair getting attached, this elimination of this nitrogen, a negative charge will be created at this particular carbon center, and into that center this alkene will migrate, and this oxygen carbon bond will be breaking, and we will get this particular compound as the major product. That is, option D is the major product. I hope it is clear. So this oxygen lone pairs will attack the center and eliminating this nitrogen molecule. So a positive negative charge will be there at the center, and that negative charge will attack this alkene, and this bond will shift to here, and this positive charge on this OH will be stabilized by this particular bond. So this bond will be cleaving, and here one bond will be forming between this carbon and this alkene carbon, and this double bond will be migrated to here. So we will get this particular compound as a major product. So here the correct answer is option D. Moving to the next question, what is a major product in the following transformation? So this particular indole derivative, upon treatment with this methylaldehyde, that is acetaldehyde, and H2SO4, what will be the major product in this reaction? So I will give a couple of minutes time to think about this. Then we will discuss the answer. So aldehyde is being treated with that particular indole derivative having an amine group at the terminal position under acid condition. So what will be the major product? So here the correct answer is option A. And I hope this answer is clear because this is pretty straightforward mechanism. That is, this amine will react with this aldehyde and it will result in the formation of this N double bond. Here it will be plus, one H will get eliminated and this will be Me. So this type of aluminum ion will be formed, and then this bond will go and attack this electrophilic carbon, and thus this positive charge on this nitrogen will be stabilized. And here we can say one OH will be there. So this bond will be forming, so resulting in that six membered ring. Then again that dehydration will take place to form this aromatic ring again. So we will get the correct answer as option A. So I hope it is clear. First imine formation or in iminium ion formation with this aldehyde and then the cyclization to form this answer A. Option A as the correct answer. That is dehydration of this alcohol will regain this aromaticity of this indole. And this methyl will be coming at this particular position. So I hope it is clear. First the intermediate will be like NH double bond CH. Here OH will be there and here one Me will be there. Then and one plus charge will be here, so that electrophilic carbon center will be attacked by this particular bond. Here one bond will be forming and then again this dehydration and rearomatization will take place to form the correct answer as option A. So I hope it is clear. Moving to the next question of assignment 9. Match the terpene molecules in column A with the number of carbon atoms in their skeleton in column B. So four options are given in column A, that is monoterpenes, sesquiterpenes, diterpenes and steroids. And in column B, C30, C10, C15, C20. So we have to match which is the correct answer for this. Like monoterpenes, how many number of carbon atoms it is having, sesquiterpenes, how many number of carbon atoms it have, similarly diterpenes and steroids with the corresponding number of carbon atoms. Okay. So the correct answer for this question is option B. That is, as we know, monoterpenes corresponds to 10 number of carbon atoms and it is usually derived from this geraniol. And the sesquiterpenes corresponds to 15 number of carbon atoms and it is derived from the terpene farnesol. And C is diterpenes, which is having 20 carbon atoms and that is derived from this geranyl geraniol. And then steroids is having, that is option first, that is 30 carbon atoms and it is derived from squalene. So we already have a detailed discussion on this terpenes and steroids in prostaglandin, in I think progesterone lectures. So the correct answer for this question is option B. And we have also seen how it is formed. That is, this is the basic reaction through which these terpenes are formed. And the isoprene is the building block of terpene, that is having 13 number of carbon atoms, and the isoprenes generally exist in nature as pyrophosphates, which are good living groups. And some examples for this monoterpenes include limonene, menthol, camphor, carvone, geraniol. So we already have a detailed discussion on this topic previously. So I will move to the next question. Identify the major product of the following reaction. So this particular compound, upon treatment with this anhydride in presence of this dichloromethane in trifluoroacetic acid condition, out of these four options, which will be the major product? So as we can see in all the options, it is ring formation reaction. That is, here only one ring is there in the starting material, but in the all options given here, four rings are forming. So which will be the correct answer for this question? Okay, so here the correct answer is option C. That is, as we can see how this rearrangement is taking place. So it is basically a ring closing type of reaction, that is aldehyde, this trifluoroacetic acid catalyzed ring closing type of reaction. So this anhydride will be favoring this alkyne attack on this alkene, and it will help in the ring closing at this position, and then it will help in the ring closing of this particular position, and here this double bond will migrate to this center, and this will be stabilized by this OH2 water molecule. So this anhydride will be helping in the making this alkyne more nucleophilic, and it will make this alkyne to attack this alkene sender, and this alkene in turn will attack at this particular alkene sender, and this double bond will shift to here, and this double bond will shift to here, and this particular carbocation will attack on the water molecule present in the system, and then this proton release will result in the, and then this elimination of this water molecule, protonation, and then elimination of this water molecule will result in this correct answer, that is option C. So I hope it is clear. Once again, I will tell this will activate this particular alkyne to attack at this center, this anhydride, that is this particular group will attack at this center, eliminating this as glycol mostly. Okay, so this anhydride will attack at this center and then this bond will be shift. Sorry for that. And this bond will be shifted to here and this bond to here, this bond to here, and this double bond will be migrating to this position, and this water molecule get protonated and it will get eliminated. So it will result in this six membered ring here, one six membered ring here, six membered ring, another six membered ring here, and an alkene that is isomerized from this position to this position along with the elimination of this OH. So that is what is happening in this reaction. Moving on to our last question of week 9 assignment. Week 9 assignment, that is question number 10. Identify the major product in the below reaction. So this particular compound, upon treatment with this palladium diacetate and triphenyl phosphine, what will be the reaction happening here? So here, as we know, the functional groups present are this double bond and then this carboxylic acid and this O tertiary butyl group, which is intact in all the three options except this one, and that position of double bond is being changed in this option A and C. Then carboxylic group is anyway getting eliminated in all the four options. So which will be the correct answer for this question? So out of these four options, which will be the correct answer for the question given here? Under palladium diacetate and triphenyl phosphine condition, what will be happening? So here the correct answer is option A, that is this palladium acetate and triphenyl phosphine condition. This CO2 carboxylic acid will get eliminated and isomerization of this double bond will take place to give option A as the right answer. So as we can see, okay, this carboxylic acid is coming in that position in the previous step by treating this particular alcohol with this formic acid in pyridine. So this alcohol will be converted into corresponding carboxylic acid. So here what is happening under palladium condition, this double bond will get shifted to here, isomerization along with the elimination of this as CO2, it will get eliminated. So the correct answer for this question is option A. So I hope it is clear. That is all about the week 9 assignment questions. So half of the week 9 assignment questions we have discussed in last class as well, where we saw this rearrangement, then this acid formation and 1,3 dipolar cycloaddition, followed by this nitrogen elimination, then this protection and then reduction of that pyridine ring, then this MCPBA epoxidation, and then this what is this? Okay, ester hydrolysis and then oxidation. Then from this carbenoid intermediate mediated reaction and then rearrangement. Then this imine formation and then ring closure. Then about terpenes and then this ring closing reaction. And the last question was the palladium mediated decarboxylation and isomerization of double bond. So that is about the week 9 assignment. Now let's move to the week 10 assignment. So the first question of week 10 assignment is identify the major product in the following transformation. So this particular compound, which is a precursor of Taxol, is treated in first step with acetic anhydride and DMAP, and in the second step it is treated with this TPAP and NMO. So what will be the major product? So TPAP is tetrapropyl ammonium perruthenate and NMO is N-morpholine N oxide. So it is basically an oxidizing agent, and this it is like a co-catalyst. NMO is like a co-catalyst, or what we can say. It will be regenerating this ruthenium catalyst, so that we have to add this particular TPAP oxidizing agent in catalytic amount only, and this NMO in stoichiometric amount. So out of the four options given here, what will be the major product? Okay, so here first what will be happening is this by treating it with this compound with acetic anhydride in DMAP condition, this we can selectively acetylate this allylic hydroxyl group selectively, so that this will remain as free hydroxyl group. So we will get the intermediate as this one in the first step. Then by treating it with this TPAP tetra, what was that, TPAP, that is one oxidizing reagent, that is tetrapropyl ammonium perruthenate. So in with NMO it will be capable of oxidizing this free hydroxyl group present in here and make it into ketone. So the correct answer will be option C. So first under acetic anhydride and DMAP condition, this allylic alcohol can be selectively acetylated. That is, OH can be converted into OAC selectively due to the presence of this allylic double bond. And then second condition, only one free hydroxyl group is there. That is the secondary hydroxyl group. So it will get protected and it will get oxidized under the TPAP NMO condition to get ketone here. So the change is that one allylic alcohol get converted into acetyl group and this hydroxyl group will get converted into ketone under these two conditions. So the correct answer will be option C. So this it is known as Lay-Griffith oxidation. That is this TPAP tetrapropyl ammonium perruthenate, and this NMO mediated oxidation is known as oxidation of this alcohol to ketone is usually known as Lay-Griffith oxidation. Moving to the next question, what are the major products P and Q formed in the following sequence of transformation? So this particular compound is treated with the sulfurylide type of compound in THF and KHMDS. So we will get P, which is then subjected to this triisopropoxide aluminium and toluene under reflux condition. So what will be the major product? We have to identify both P and Q in this reaction. So here what will be happening, first this sulfur halide will make this ketone, convert this ketone into corresponding epoxide. So we can see in the first step the answer will be this one. So here the correct answer is option A. So in the first step this epoxide will be forming. Then what will be happening is this epoxide ring will open under this triisopropyl aluminum mediated condition, and then this deprotonation will take place to form this double bond. So this is how we will get this corresponding this product, that is option, that is product Q, is this one. So the correct answer is option A. So sulfur halides are basically used for the epoxidation of ketones. So, and in the second step, this aluminum triisopropoxide mediated opening of the epoxide and then deprotonation will give this double bond. That is when this epoxide will be opened from this position. Here a positive charge will be generated which will be stabilized by this deprotonation. So here double bond will be forming after the epoxide ring opening. So I hope it is clear. So the major products are this one corresponding to option A, first epoxide, and this epoxide ring opening with this formation of this double bond. Moving to the third question, identify the major product in the following transformation. So this particular compound upon treatment with NCPBA and in DCM condition, which will be the major product. So as we know, there are two double bonds and NCPBA is used for the epoxidation of course. So out of these two double bonds which will be getting epoxidized, and what will be the correct stereochemistry of that? So here, as we know, MCPBA will be epoxidizing the electron-rich double bond. So this double bond, this particular double bond that is in the alpha position to this carbonyl group is electron deficient due to the presence of this ketone. And obviously, this double bond is more electron rich than this particular double bond. So epoxidation will be taking at this position. So the correct answer is option B. This is the correct answer. And as we can see, due to the steric hindrance, this epoxidation will be taking place from the above side, that is from the beta phase rather than the alpha phase. So the correct answer will be option B. So here, as we can see, it is evident that this MCPBA epoxidation is not directed by this hydroxyl group. It is usually depend. It is here depending on the steric factor only. Moving to the next question, which is the major product formed in the reaction given below? That is, this particular compound, upon treatment with the samariamide in acetic anhydride condition, which will be the major product in this reaction out of the four options given here. Okay, so here what is happening is that the correct answer is option D. And how it is going through is the samarium iodide mediated this ring opening of this epoxide ring opening, and then further this acetic anhydride will help in the dehydration, that is this OH, and this proton from here will eliminate to give this corresponding double bond at this position. So that's how this is getting formed, that is this alpha beta unsaturated ketone will be forming from this epoxide. So I hope it is clear. So this epoxide ring will be opened by samarium iodide, which is a one electron donor, and then acetic anhydride mediated dehydration will take place in the formation of a double bond at this position. So moving to the next question, identify the major product of the following transformation. So this particular compound is first treated with this tertiary butyl peroxide and then titanium tetraisopropoxide in DCM, and in the second step with BF3 etherite and this trifluoromethane sulfonic acid in DCM. So what will be the major product out of this four options? Okay, so here the correct answer is first With this, like similar to MCPBA, with this peroxide also an epoxide formation will take place, which is directed by this hydroxyl group. Then this BF3 etherate, being Lewis acid, it will coordinate with this epoxide oxygen, and here from here this deprotonation will take place, and this bond will shift to here, and this particular bridged bond will be shifted to here, and this epoxide will be open to give this product. Then again dehydration will take place. No, so this is the correct answer, that is option A. So I hope it is clear. So in the first step, what is happening is epoxide formation of the double bond. Then from here, that is alpha, this beta position deprotonation take place by when the BF3 etherate coordinate with the epoxide, and this bond will be, this deprotonation will create a double bond at this position, which gets shifted to here, and then the epoxide ring will be open to get this alcohol. So here the correct answer is option A. Moving to the next question, that is sixth question. What is the major product formed in the following transformation? So this particular compound upon treatment with red dalene toluene at minus 78 degrees Celsius, which will be the major product out of the four options given here. So here what is happening is this radal will, it is a reducing agent, so it will reduce this ester as well as this ketone to form this diol. So already this hydroxyl group is here, so it will result in this triol. So radal is used as an reducing agent in this case. Okay, so the correct answer is option C. This ketone and this ester will be reduced by this radal, giving this triol. So the next question is, that is the seventh question. Identify the major product formed in the reaction given below. So this particular compound, upon treatment with this phenyl selenium derivative and tertiary butoxide condition, then again with tertiary butoxide, potassium tertiary butoxide in THF, which will be the major product in this reaction. So here what is happening is, first this will be converted, that is here an OH will be installed by this phenylselenium reagent, that is here at this position, and then on the treatment with this potassium tertiary butoxide, this rearrangement will happen, that is actually this OH through the enol formation, this OH and ketone will interchange its position to get this particular compound. So the correct answer here is option A. That is, this phenylselenium bromide and phenylselenium complex are commonly used for the alcohol hydroxyl group generation at the alpha to carbonyl center. So that will be happening in the first step, and in the next step, that is in the first step, this compound will be formed with hydroxyl group at this alpha carbonyl position, and then in the next step, when treating with this potassium tertiary butoxide, through the enol formation, this will get rearranged and we will get hydroxyl group at this position and ketone at this position. So this will be the major product in this reaction. That is, correct answer is option A. Moving to the next question, identify the major product in the following transformation. So this compound is treated with potassium tertiary butoxide under oxygen atmosphere and this triethoxy phosphorus in THF, and in the second step with ammonium chloride and methanol. So out of this four options given here, which will be the major product? So here the correct answer is option C. So what is happening under this potassium tertiary butoxide condition? Proton will be abstracted from this alpha center, and here anion will be generated, and that will create this ethoxy group to attack at this position, and then this ammonium chloride will convert it into corresponding hydroxyl group. So this is one another method, like as we discussed in previous question, to install hydroxyl group at the alpha carbonyl position. So the correct answer will be option C. So I hope it is clear. So this anion generation at this position and then hydroxyl group will be installed at that position to get this corresponding product, that is alpha hydroxy ketone. Option C will be the major product. Next question is identify the major product of the following reaction. So this particular compound upon treatment with this guanine derivative in DCM, which will be the major product of this reaction. So here this guanidine derivative will helps in this. So this is that step will helps in the rearranging, as we said earlier, rearranging of this acetyl group and this ketone. It will just swap its position through the enolide formation. And here also the correct answer will be option A, that is this, they are just interchanging this positions through rearrangement. So I hope it is clear. Moving to the last question of week 10 assignment. What is the major product in this following reaction? So this methoxybenzene is treated with the succinic anhydride in aluminum trichloride DCM condition, which will be the major product out of this four options given here. Okay. So here what is happening is with the succinic anhydride, this free Craft acylation will be taking place, resulting in this particular compound. The correct answer will be option C. That is a Friedel-Crafts acylation of this methoxybenzene with this corresponding succinic anhydride in presence of the Lewis acid catalyst aluminum chloride in DCM. We will get the acylated product. So the correct answer is option C here. So that was the 10 question of week 10 assignment. So I will give you some time to go through these questions. Then we will move into the discussion on last week's week 11 lecture contents. Okay. So now let's move to the discussion on the week 11 lectures. So the first two lectures, lecture 50 and lecture 51, was about eleuthrobbing. So let us first discuss about week 50 lecture, eleuthrobbing, that was total synthesis by Nicholas group, where we saw the application of intramolecular acetylide addition, non-conventional condensation, and glycosylation to total synthesis of eleuthrobbing by Nicholas. And this eleuthrobin is an anti-cancer agent, that is an anti-tumor agent with a mechanism of action like Taxol. And it was isolated from an Eleutherobia species of marine surf corals collected in the Indonesian near Bennett's Shoal in Western Australia. Then this eleuthrobin poses significant cytotoxicity against a variety of cancer cells, and it was shown to be a potent cancer cell inhibitor with an IC50 range of 10 to 15 nanomolar in vitro against a diverse panel of tumor cell lines. It was found to stabilize microtubules by competing for the paclitaxel, that is Taxol, binding site on the microtubule polymer. And the tumor tissue selectivity of eleuthrobin determined in the National Cancer Institute 60 cell panel showed an approximate 100-fold increased potency towards selected breast, renal, ovarian, and lung cancer cell lines. So, as it is evident from this structure, the structural challenges involves this tricyclic ring, that is 6, 9, 5, with chiral centers in the core structure as well. And then the another challenge is the construction of this 9-membered ring with 6 substituents. Then overall 10 chiral centers are present. That is also a synthetic challenge. Then it has two side chains. One contains the EN6 dash urocanic acid residue, and the other beta linked to acetyl D-arabinopyranose unit. So the first order synthesis was reported by Niccolo in 1997, which allows assignment of absolute stereochemistry of eleuthrobin. The key reactions are intramolecular addition of acetylide, reduction of triple bond, and subsequent cyclization to form 5 and 9 membered rings. And the synthesis started with the commercially available monoterpene plus carbon. So this AB ring is a 6-9 fused bicyclic system. BC is a 9-5 fused bridged bicyclic system, and ABC is a 6-10 fused system. So Nicholas group completed the total synthesis in 27 steps with an overall yield of 0.9%. Then the second discussion was about the total synthesis of eleuthrobin by Danishevsky, that was lecture 51, where we saw the application of Nosaki-Kishi ring closure, pyranose to furanose transportation, and Stille coupling to total synthesis of eleuthrobin. So Danishevsky and co-workers completed the total synthesis of eleuthrobin in 1998, starting with R minus alpha philandry. And the synthesis rigorously proves the relative stereochemical relationship of the diterpenoid and carbohydrate domains of eleuthrobin. The key reactions, as we told, it is Nosaki-Kishi ring closure to produce a furanophane, pyranose to furanose transposition, and Stille coupling for joining the two domains. And this Nosaki-Hiyama-Kishi reaction is a which we have discussed previously also. It is a nickel-chromium coupled reaction forming alcohol from the reaction of an aldehyde with an allyl or vinyl halide or triflate. Then this inter and intramolecular variations have been reported which have additional importance when this methodology is applied to natural product synthesis. And the organochromium reagents formed are unisolable from the corresponding halides and chromium 2 chloride or CrCl3 and LAH. So this eleutropin synthesis by Danishevsky started with R minus alpha philandrine, and he completed the total synthesis in 26 steps with an overall yield of 0.25%. So that was about the first two lectures, lecture 50 and 51. So the next discussion was about lecture 52, which was about four ball, where we saw the total synthesis of four ball by Vander's group, and in which utilizes the application of oxidopyrrolium alkene cycloaddition. And four ball was first isolated in 1934 as a hydrolysis product of croton oil, which is derived from the seeds of purging cotton, croton triglyum. However, croton triglyum. However, the structure of four ball was determined only in 1967. And these four-ball esters have been vigorously studied over the past half century since the discovery that this non-carcinogenic compounds completely amplifies the effect of certain carcinogens in animals. It is proposed that the four-ball ester promoters active protein kinase, that is PKC, a key enzyme which mediates cellular signal transduction, initiated by numerous effectors including hormones, neurotransmitters, growth factors, and oncogens. As a consequence, this pathway PKC and the four-ball esters have emerged as important leads in the formation of a molecular mechanism for carcinogenesis as well as in the development of chemotherapeutic agent for cancer and other disease, most notably including AIDS. Venter et al. Reported the first photosynthesis of four-ball in 1989, starting with furfuryl alcohol. And the problems posed by the eight stereogenic centers of four-ball and exacerbated by its highly congested and highly reactive functionalities have each been selectively solved with 93% overall stereoselectivity. So the key reactions, as we told, are oxidopyrrolium alkene cycloaddition reaction to get this 5,6 fused system of four ball. And he took 53 steps to complete this total synthesis, and the overall yield was 0.19%. Then the next lecture was about periplanon, where we saw the application of anionic oxycop rearrangement in the total synthesis of periplanon by Still, and anionic oxycop rearrangement intermolecular 2 plus 2 photocycloaddition in the synthesis of periplanon B by Schreiber. So this is the structure of periplanon B. So in 1952, it was reported that a constituent of the excretion from female American cockroaches of the species Periplaneta americana is an extraordinary potent sex pheromone. Early attempts to isolate and characterize the active compound were hampered because individual cockroaches store only minute amount of pheromones, that is very less than 1 milligram, and a full 25 hours elapsed before years elapsed before persons at all reported the isolation of two extremely active compounds, periplanon A and B. So moving to the Still's total synthesis of periplanon B, Still's periplanon B synthesis provides a striking demonstration of the power of anionic oxycop rearrangement for the synthesis of cyclodecanoid framework that is given in the structure, and the flexibility of organic synthesis allowed the preparation of three different diastereomers of periplanon B and conclusively established the structure and relative stereochemistry of this molecule. Still's periplanon B synthesis provides a striking demonstration of the power of anionic oxycop rearrangement for the synthesis of cyclodecanoid framework. In this beautiful synthesis of periplanon B, Still demonstrated a classical aspect and use of total synthesis for the unambiguous establishment of structure of the natural product. And the starting material used is ethoxyethyl ether of 5-hydroxymethyl cyclohexanone. And the Still's group could complete this total synthesis in 15 steps with 8.92% of overall yield. Then in Schreber's total synthesis of periplanon B, in 1984, Schreber and Chantini developed an efficient and elegant synthesis of periplanon B, the potent sex pheromone of American cockroach Periplaneta americana. And Schreber's approach to periplanon B takes full advantage of the facility with which functionalized 5-cyclodecaine 1-on systems can be constructed via anionic oxycop rearrangement of readily available divinyl cyclohexanol. And the starting material is 4 isopropyl 2 cyclohexene 1 on, and he completed this total synthesis in 13 steps with 1.75% of overall yield. Then the last lecture, lecture 54, was about discodermalide, where we saw the application of Corey's asymmetric reduction in total synthesis of minus discodermalide by Schreiber, boron mediated aldol reaction, the total synthesis of plus discodermalide by Pearson. So here, the scientists at the Harbour Branch Oceanographic Institute have reported the discovery and structural characterization of this marine natural product discodermalide, and this compound inhibits the proliferation of cultured lymphocytes, making it a candidate for use in immunosuppressive therapy. And then we have seen the Schreiber's total synthesis of minus discodermalide. Schreiber and co-workers reported the first total synthesis of this minus antipode of discodermalide in 1993. And the plan for their synthesis hinged on the recognition that three fragments of roughly equal complexity are separated by olefinic units in discodermalide. The starting material was methyl R minus 3 hydroxy 2 methyl propionate. And this Schreiber's group could complete this total synthesis in 24 steps with 3.2% of overall yield. So that was about the discussion on last lectures, lecture 54. And this time also, I haven't included the Reiki reactions because almost all the reactions mechanism we have discussed, like Ekmatovich rearrangement, nominal condensation, that I have just included. But this also we have discussed previously. So now maybe you can go through the lecture contents for a couple of minutes and the mechanisms of the reactions that we have discussed and the questions as well, and then we will be winding up the today's session, tutorial session. Okay, so that's about today's tutorial session. So we have discussed week 9 assignment and week 10 assignments as well as week 11 lecture contents. I hope it is clear and helpful to you. So next class will be mostly our last tutorial session. So if you have any queries regarding this tutorial sessions till now, you can ask or you can post in the NPTEL portal as well. So thank you for listening. Thank you so much. See you.